Some special types of matrices have what are called matrix inverses. And in that case, we say that the matrix is invertible. Now, there's a couple of key points here with, first of all, dealing with a matrix inverse. The first being that this is only going to deal with a special case. So the requirement is that A, our matrix that we're trying to find the inverse of, must be n by n, meaning it has to be a square matrix. It has to have the same number of rows as it does columns. And the reason is going to be something that we'll discover here shortly. But let's motivate this first. Let's say we want to solve the matrix equation AX equals B, which we know we could take the columns of A and the B vector, put them in a augmented matrix, perform row reduction or Gaussian elimination, and thereby getting the values of the variables in the X vector. But let's think about it another way. Let's think about the familiar algebraic equation 3x equals 12. Now we know that here there are a couple of ways to solve this. One way would be to divide both sides by 3 and to get x equals 4. So if we try to do that same thing here, we'd run into a problem, and this would be problematic already because there is no matrix division. And there's a couple of reasons for that. One, it's not a very useful operation. And two, if you think about it, B is a vector and A is a full-on matrix that has n rows and n columns. B is a vector it's going to have n rows in one column. And so this is just not going to make any sense to do this. We have an n by 1 divided by an n by n. It just doesn't make any sense. Even if they were similar dimensions, it wouldn't mathematically make sense. And I'll leave it at that. So what other ways do we have of solving this? Well, one other way is to think about not division by 3, but multiplication by what we call the inverse of 3. Okay, so if we have the inverse of 3, and we multiply both sides by that, well, the inverse of 3 is really just 1/3. And 1/3 of 3 is 1, and so we get 1x equals 1/3 of 12, which is 4. So effectively, this right here cancels out and gives us the coefficient of 1. If we repeat that same process, now it turns out that there is such a thing as a matrix inverse. If we take AX equals B, and we multiply both sides by A inverse, keeping that matrix on the left is very important, because if we multiply it over here, then we're going to have dimensional problems. This is going to be an n by n, so will this. This is going to be an n by 1, and this will also be an n by 1. Okay, so what we're doing here with this square idea is that we have the same number of equations as we do variables. Okay, so same number of equations as variables is ultimately what the square matrix is getting at. So if you have two lines and two equations, then they could have a single intersection point. Okay, well, if we do it on the left, we have to do it on the right. And again, I just have to keep it on. This may seem weird because really it didn't matter where we multiplied 3 inverse on the left and the right over dealing with this algebraic equation. But because the order of matrix multiplication is important, A inverse is an n by n. So if you put it over on the right and made this B times A inverse, you'd have an n by 1 times an n by n, and that's a dimensional mismatch. Okay, so what's going to happen here? Well, the idea will be that A inverse times A cancel out in a similar way. But notice that the dimensions of this product are going to be n by n. So it's not going to produce a scalar, it's going to produce a new matrix. Well, what matrix do we know of that is like a 1, that acts like a 1? That, in other words, anything it multiplies, it does not change it. It's the identity. Well, oh, there it is. It's the identity matrix. We want that product to be the identity matrix. so that the identity times any vector or any matrix, this is an n by n times an n by 1, which will give us an n by 1. So this product right here is just equal to x, just like we could write 1x equals 4 as just x equals 4. And we've just solved for the vector x. We've just found out that to solve for x, we have to multiply the inverse of a times b. Now, if, just one important note, if a is equal to, say, 1, 2, 3, 4, then it is not the case, I'm going to say A inverse is not simply 1 over 1, 1 over 2, 1 over 3, and 1 over 4. It's not quite that simple because matrix multiplication is not quite that simple. Okay, so that's not how we find it. It's not a trivial process that we have to go through. But we'll discover that. In this video, we're just focused on setting up the basis, the foundation, the motivation for finding an inverse matrix. Okay, so what we need is an inverse matrix such that when you multiply A by A inverse, you get I, as well as if you take A inverse times A, you want to get I. It's kind of like saying, well, 1/3 of 3 is the same thing as 3 times 1/3, and both of those equal 1. So same kind of idea here. The order should not matter. And these are both n by n, which is important because if you reverse their order, the product is still going to be an n by n identity matrix. And that is why A must be square in order for this to work out, because let's say that A was m by n. It had m rows and it had n columns. Well then A inverse would still be an m by n matrix, but this product cannot be found because there's going to be a dimensional mismatch. Not only that, but let's suppose that you did find an inverse, and the problem with this would be that if you took an m by n matrix and you multiplied it by b, which is an n by 1 vector, and now you obtained an m by 1 result, that's not going to work because x, I'll say that's not equal to the vector x, which is what we're trying to solve for, which is an n by 1. It has n variables, and it has m equations. So we're going to be, even if we could find an inverse of such a thing, we'd have problems with dimensionality. So we can say A is square to avoid dimensionality issues. We'll just leave it at that. Now here's a key result from this. If such an inverse exists, then we say that A is invertible. Okay, so it doesn't always exist. We'll see when it doesn't. And the system will have a unique solution, one solution. And this is kind of easy to see if you just think about the equation that we derived to solve for x. Well, if A inverse exists, this is going to have some numbers in there. Let's just say this is a 2 by 2 system. And this will have 2 numbers in it. And when we multiply and add those together, we're multiplying and adding numbers that are determined, and so we're just going to get 2 new numbers in this product, and therefore x will be distinct. The values of, maybe we can call these x1 and x2, those values are going to be distinct. Meaning, the vector will be distinct. The values could end up being the same. Maybe they intersect at x equals 5, y equals 5. But the vector x will not generate more than one solution as long as A is invertible. If A inverse doesn't exist, this whole method is not worth a dime, and it's worth forgetting about in that case. So why do we use the inverse? Well, it is useful in contextual information where, as we'll see in another lesson, there is a real-world meaning sometimes tied to matrices, which could actually be the elasticity of beams, for example, in a mechanical infrastructure. In the Leontief model that we'll study, it has something to do with prices and quantities, and so there is usefulness in it. It's just if your sole goal is to solve a system of equations, you don't really need to go through all this hassle.